Here we are in section 8.1.2. We're going to talk about left, right, and two-tailed tests, and we're actually going to see how to find p-values. Now, here's the point. Determining the p-value. Here's the definition. The p-value of a hypothesis test, that is the probability of observing a test statistic with a value as, or even more, extreme than the one determined from the sample. Now, you might read that again, you might read it again, but why don't we see if we can interpret this with an example. Now, I just did this one all at once, so let's just go over it here. This one is called a left-tail test. We're going to do 3 examples. First of all, getting the p-value if you're using a left-tail test. Secondly, getting the p-value if you're using a right-tail test. And then our last example will be getting a p-value using a two-tail test. So first up, a one-tail test, a left-tail test. Suppose that you're testing a claim that the mean is, say, greater than or equal to some number. I'll just use k. It could be anything, like maybe 170. All right, versus the alternate hypothesis that the mean is less than that number. So you can see the less than symbol, meaning pointing to the left, so we're going to have what's called a left-tail test. Now the p-value is the probability of getting this number here or something more extreme. By more extreme, we mean farther out. And that turns out to be the area to the left of that z star. That's our computed value there, our test statistic. Here's an example. Suppose that we're going to say that the null hypothesis is greater than or equal to 2.6 versus that it is less than 2.6. We take a random sample of size 61 and we compute the sample mean to be 2.4 and the standard deviation to be 8.5. Now the alternate hypothesis is a less than 2.6. Our observed mean is 2.4, so there is some evidence that the mean might be smaller, now less than, the 2.6. Well, it makes sense to continue on with the test. Now what I have to do is I have to choose my alpha value, so I'm going to choose 0.05, which means what? That we're willing to reject H naught. If this is true, we're going to reject it 5% of the time. Now, I'm going to run my test statistic, all right? Z star, I'm going to standardize, so Z star is X bar minus mu. I'll put mu naught to remind me that that's the number I put in, divided by sigma over square root of n. Now, I don't really have sigma, right? We have S, but I got a large sample, so I can replace sigma with S. So I will use 2.4 minus 2.6 divided by 0.85 over the square root of 61. Now, make sure you can get this right on your calculator. So I've got a fraction, and this fraction has a top and a bottom. The top has an operation in it, subtraction. The bottom has an operation in it, division. So I'm going to set those off in parentheses, right? Group the top together, group the bottom together. So back over here on the bottom left. Parentheses, open up the bottom. 2.4 minus 2.6. Close. That finishes off the top. Press the divide key. Now you have an operation in the bottom, so open it up. Open up the bottom with the parentheses. 0.85. Press the divide. Now you have to press second x squared to get the square root key on the very left column. And then type in 61, and then use your arrow key to get out of the square root. Then type another parentheses. And when you do that and press enter, you come up with about negative 1.84. Now let's get the p-value. Here we are, finally getting that p-value. So remember what p is up here at the top left. P is the probability, the area to the left of z star. All right, now I got my z star value, negative 1.84. So I'm going to draw a picture here. Here's a picture. Here's the negative 1.84, and here is the area to the left. Now, you may remember doing this, but just in case, here's what you do. You want the area under the curve to the left of that z value. So go to second on your calculator, go to second, vars. That's really distribution. So select item number 2, normal CDF. Now, that will give you the area under the curve between two values. Now our value, so you go ahead and select it, and this is what comes up, normal CDF, and you get a parentheses. Now our values, our lower value is negative infinity. The upper value, the right-hand value, is negative 1.84. So we got to get that negative infinity in there. Now you probably could type in something like negative 100,000, but if you really want to get closer to negative infinity, you type in negative E99. Now where do you get this negative E99? Well, the negative, this is the negative key. All right, now the negative key, that negative key, I'll do it down here at the very bottom. That's at the bottom of your calculator to the right, you'll see a negative key. It's in parentheses. It's not the minus key, it's the negative key. So press negative, then, now you want this E, that's the exponential. So where is that? Well, it's above the comma. So, but it's the second function. So you got the negative, press second, comma, that'll give you, it says EE, but you get only one E. So negative, second, comma, EE, and then type in 99. That'll get you this. It's like times 10 to the negative 99. Or negative 10 to the 99th. It's way out to the left. All right, that's your left limit. Then put a comma right above the 7. Type in negative 1.84. Now you really don't need anything here. If you left it off, you'd be okay. But you can write a comma and then 0 for the mean of the standard curve, which is 0. And then comma 1 for the standard deviation of the standardized curve. When you do all that, you press enter, you get 0.0329. That is the p-value. So we finally see how to get it. So the p-value is 0.0329. And that gives us the area right there. That is the area under that part of the curve. So now what do? Do we reject H0 or do we not reject H0? Well, here's what we do. We compare P to alpha. So let's do this. Compare P to alpha. I like to set up a little table. There's P, alpha. Now the P was 0.0329. Alpha we've set to be 0.05. And I can see that 3% is less than 5%. So I got a less than there, right? Less than. That blue doesn't show up too well. Now, you may remember what we did in the last section. Well, what we said was this. I see a less than, and that means, to me, smaller. So we said the smaller the p-value, the less likely some event is to occur. And less likely means, to me, it's unlikely. And if it's unlikely, I'm going to reject H0. So I'm thinking this. I'm willing to reject a hypothesis up to 5%. But we're only at 3%. So 3% is even less than the 5%. So I'm willing to reject. So I'm good with this. So I'm going to reject H0. And then if I remember my table, it says this. If P is less than or equal to alpha, you reject H0. Now, if you can remember that, that's great. I go through this little bit of thinking so that I can remember this. Now, let's get the p-value directly on the calculator. So here's our problem, right? This is the one that we're dealing with. So H0 states that the mean is greater than or equal to 2.6. The alternate is that it's less than 2.6. Here's the data that we had. All right, now to get the p-value directly on your calculator, what you're going to do is you're going to press the stat key, and then you're going to arrow over to tests. So stat over to tests. You're going to choose item number 1, which is z-test. And then you're going to choose stats. All right, we're putting in statistics, not data. So you press stats, select stats, and then press enter, and then you have to put in these numbers. All right, mu naught. Now mu naught is H0. It's just the calculator's way of saying it. So you're going to put in 2.6. That's what we're testing. Sigma. Our sigma is 0.85. Then you're going to put in X bar. And the X bar is 2.4. Forgot what it was for a minute. And then N is 61. Oh, it's not an equal sign, right? Is 61. Now we are doing a left tail test. If you remember this, we're doing a left tail test. So down here it says mu, and then it says not equal, less than mu naught, greater than mu naught. So we're going to select this one here. We're selecting a left-tailed test. Then we're going to go to calculate. Now here's what came up on my calculator. I got mu less than 2.6. It's just reminding me what I'm testing. I got a z value. Now this turns out to be the z star value. There's our negative 1.84. So the calculator actually does it all for us. But here's what we're looking for. Here's the p value, 0.0330. Now when we did this by hand, we got 0.0329, but that was rounded off a little bit. So now this actually gives us the p-value without doing hardly any work. So just to finish it off, I'm going to compare p and alpha. This is just what we did before, but I got 0.0330. Alpha is, I think we did this at what? 0.05? I think we did a 0.05. So this is less than this. Now I'm seeing a less than. I'm seeing a less than. So if I see less than, I'm thinking small p, less than, small p. That means small probability, which means, but I'm seeing it, so it's unlikely. And if it's unlikely, I'm going to reject H naught. Let's do an example now of how to get the p-value when we run a right-tailed test. A right-tailed test is going to occur when somebody makes a claim, say, or somebody's thinking that, oh, the mu is now greater than what it used to be. So we're going to write our alternate hypothesis as a greater than, and just mathematically to keep everything on the up and up, so we have all numbers included, we'll say not just that it's equal to k, but say that it's less than or equal to k. So we're going to run a right-tailed test. So I'll draw the curve, and that means I'm going to put all my area, all the probability there in the right tail. And that means that that area right there, that is the p-value. So let's find it. I'm going to do this directly on the calculator now, and actually let's do it using that example that we've been using. The one we've been using is that H naught states that the mu is, say, less than or equal to 2.6. H sub A, now let's say that its mu is greater than 2.6, so we'll have to make up some data so this thing works. Suppose now that X bar is, I'll just put in some data here, so maybe it's like 2.64, all right, let's just pick a number now. S will turn out to be 0.85 again. I'm just choosing a new X bar, one that's greater, so it puts me in the right tail. And N is 61 again. And this time, let's choose alpha. Last time we did 0.5. Let's choose it to be 0.01, just to see what happens. Now, go to Stat, over to Tests, select number 1, Z-test. Select statistics, because we're not putting in data, we're just putting in the statistics. Mu naught, that's what we're testing, 2.6, probably there from the last time we did this. Sigma, 0.85. But now X bar, this is different than the last example. Last example, I think it was 2.4. But now we have 2.64, so put in 2.64. N is 61. And now for mu, what you want to do, we're doing a right-tailed test. So you see how this goes. It goes not equal to mu. I think it goes less than mu. And then over here, it's the right is greater than mu. So you want to select that one. So select that one. Then you go to calculate. And then when I calculated, I got my p-value to be 0.3566. Now, actually, here's what came up, right? Here's what comes up on your calculator. Mu is greater than 2.6. It just tells you, reminds you what you're testing. It gives you the z value. It doesn't give you z star. It gives you z, which is z star, 0.3675. But then it gives you the p-value. That's what we're after, 0.3566. All right, that's the point of this. We're able to get the p-value pretty easily just by typing in some data. But let's finish it off. Let's compare. What do we do? Do we reject or fail to reject? Compare p to alpha. All right, so a little table. That's what I like to do. P is 0.3566. Alpha in this case was 0.01. Now, 35% is bigger than 1%. So this is certainly a greater than. So we've got a greater than. Now a greater than, when I see greater than, I'm thinking large, a high, a big number. I'm thinking a high number, but I'm dealing with p-values, prob values. So this is a high probability. And if it's a high probability, that means that it is not unlikely. Right, it's likely, but I'm going to write not unlikely. And if it's not unlikely, then I will not reject H naught, so do not reject. So what I would say here is fail to reject H naught. So lastly, in our third example, let's run a two-tailed test. So H naught, H sub A. Now suppose that we've got some parameter and we just, for some reason, think that it has changed. We don't know or really care if it's up or down. We just think it's changed. So I'm going to take the parameter, maybe it's mu, and I'm going to write that it's not equal to, some value. Now because I write that it's not equal to some value, then I'm just going to write this one is equal to that value. Now this is called a two-tailed test. Here's the picture that goes along with this two-tailed test, is we will take our normal curve, and then as it turns out, our p-values, there's going to be two of them here. They're going to be right here and right here, but because we're taking p, it turns out that this is just p, actually I'll write it 1/2 p, 1/2 p. So whatever gets reported as our p-value, we got 1/2 of it in each tail. Now let's do a numerical example with the one that we've been using. So how about if H naught states that, H sub A states that. Now suppose that we say that mu is not equal to 2.6. All right, then H would state that mu is equal to 2.6. And suppose now what we have is that x bar is equal to, I'll just make this up, 2.86. Okay, I'm just making that one up. S will still be 0.85. N will still be 61. And why don't we let alpha, how about if we just choose 0.01? So we'll do this all on the calculator. We know what to do. Press stat, arrow over to test, select number 1, which is the z-test, and we want to input stats, right? Input statistics, not data. All right, so what are we going to put in here? Probably have it left over from last time. We're testing H naught is at 2.6. Let's put in 0.85 here. Now this time let's put in, what are we going to put in here? I've got it down here. 2.86. So let's put in a 2.86 here. N will still be 61. Now this mu, all right, the first one on the left is a not equal to mu naught. That's the one we want to choose. That's our two-tailed test. And when I calculated, here's what came up on my display. Mu not equal to 2.6. To remind me I'm doing a two-tailed test. The z star value, that came out to I'll round off, 2.39. And here's my p-value. The p-value is 0.0168, 0.0168. Good enough. Okay, there's my p-value. But now what to do? So let's compare p to alpha. All right, so the p is 0.0168. The alpha, I think we chose 0.01. We did. Now how does p compare to alpha? Well, this is 1.6%, this is 1%, this is just slightly bigger. So when I see that bigger, that greater than sign, when I see this, I'm thinking one number is higher than the other, so I write high. This is a high probability, and if it's a high probability, I'm thinking it is not, okay, it's high probability, so it's not unlikely. And if it's not unlikely, I do not reject. So in this case, I would fail to reject H naught. Let's erase some of it because I want to just try this. What would happen instead of using 0.01 for alpha? What would happen if we let alpha be 0.05? Okay, in that case, when I compare P and alpha, I get 0.0168 and 0.05, right? I'm going to use 0.05 this time. Now in this case, 1%, 1.68% is less than 5%. The opposite of what we just did. But now when I see a less than sign, less than, I'm thinking small, but I'm dealing with p-values, so this is a small probability. And if it's a small probability, that means that it is unlikely. Right? Something has a small probability, it's unlikely. But I'm seeing it. So I think, okay, I'm seeing something that's unlikely. So I'm going to reject H naught. So this is interesting, don't you think? You can have two people running a hypothesis test using exactly the same data. And depending on what level of significance you use, you can have, down here on the bottom right, you can have one person failing to reject the claim, but you can have another person rejecting the claim. So you can get two different values, two different conclusions using the same data.